this lecture we will discuss about 3 different types of island detection techniques. One is active island detection technique, and the second one is hybrid island detection technique, and third one is the communication based technique. Now, in the previous lecture we have discussed regarding the passive island detection technique. Then the major drawback of this particular technique is the NDZ problem. The non detection zone is very high. I mean, it is very difficult to overcome. Suppose if power mismatch is 0%, then it is very difficult to detect the islanding of the microgrid system. So, that is why the alternative another technique, which is active island detection technique, and there are number of techniques are available as far as the active islanding detection technique is concerned, and also we have many number of hybrid island detection techniques are now developed, and communication based technique those are in basically very premature stage. This wide area monitoring system, PMU or micro PMU, they are going to play a great role as far as the communication based island detection technique is concerned. Coming to this active island detection technique, here if you see that the first type of active islanding detection technique, that is a signal injection based technique. And in this technique, the signal injection based technique, what we do basically we inject the signals like disturbance signals with low frequency or high frequency also sometimes, or sometimes also we inject negative sequence signals or pulse signals through the inverter controllers. In case of solar and wind system, we have inverters, and the controllers are also present for the inverter system. And what we do in active island detection technique, we inject intentionally some disturbance signal with low frequency or high frequency to the controller of the inverter system. Now, after injecting this disturbance signal, we measure the electrical quantities or parameters at the terminal of the PCC, that is the common coupling point of common coupling. After measuring those quantities and parameters, then we will decide whether this microgrid is islanded or it is not islanded. Now, coming to this positive feedback based techniques, there basically what we do, we basically provide some parameters or quantities like voltage phase angle as a feedback to the controller of the inverter circuit, and from there again we measure the voltage and current parameters, voltage and current quantities like at the PCC bus, and then we decide whether this microgrid is islanded or not. Coming to the first active island detection based technique, that is signal injection based technique. If you could see here this figure, here we have taken the grid connected mode of operation of the microgrid. This is our grid and this is our renewable energy source. This VSC stands for voltage source converter system. Those are basically the solar systems or wind system, and here this one is our load. During the grid connected mode, we just inject this I disturbance with certain low frequency, let us consider that is 30 hertz. If our fundamental frequency is 60 hertz or 50 hertz, and we are injecting a disturbance signal of 30 hertz. And these are the currents, harmonic currents, and those currents appear due to the presence of nonlinear loads or maybe electronic components or electronic devices in the circuit. These renewable sources are basically having the electronic gadgets, electronic components. So, due to that this harmonics are basically present in the system, and this is our fundamental signal I 60 hertz or I 50 hertz. Next, this currents, if you see the impedance of this load path basically is high, and the impedance of this source path is low, and if you could see from this side, from the right side, and we can make it the source as short circuit path, and there this as a result the 60 hertz component is going to flow through the load and the I disturbance I harmonics are going to flow through the grid side terminal. And during this islanded mode of operation, islanded operation means our circuit breaker at the grid side is open. As a result, this grid current is 0, I is equal to 0 in this case during the islanded mode of operation. What happens during this condition? This I 60 or 50 hertz signal and I disturbance including the harmonic components also flow through this load. That is what the difference between this grid connected mode and islanded mode of operation. So, as a result what will happen in this case, in the first case this PCC voltage is governed by the grid, but however during this islanded mode of operation this PCC voltage is basically due to this some disturbance and 60 hertz signal. So, the voltage which is due to this disturbance signal or harmonic signal, so we can measure always the harmonic voltage at the PCC and then corresponding detection process can be developed. Now, the first one as I discussed that we inject like low frequency signal or high frequency signal. Here I have taken like I30. I30 is basically current signal with 30 hertz and this is our fundamental current signal I60. And during this grid connected mode, this I60 is going to flow through the load and I30 is going to flow through the grid side. But when it is islanded, then together this I60 and I30 are driven through the load path, and at this PCC common coupling point we will see that what is the value of this particular harmonic voltage or harmonic current signals. This is how this block diagram shows some portion of the controller for the solar system, and you can see here how this basically disturbance signal is injected to the controller of the inverter circuit of the solar system. This is our ID reference, this is basically the D axis low frequency signal injection. What we do that with a low frequency this ID, this direct access current is injected to the controller of this inverter of the solar system, and after that the corresponding this V ABC star, that is after converting this DQ component of the voltage to ABC component like ABC frame, there we can always measure this V star ABC. So, in our hand everything is there, we can see like VQ, VD, VA, VV and VC. So, due to this injection of the disturbance, what is the impact on particular this PCC voltage, that is your VABC or VQ or VD, and from there we can always determine or we can decide whether there is islanding situation or there is non-islanding situation. And this is how looks this particular ID, and this is ID is actual current and this ID star is the disturbance current, and IQ we are not going to disturb. After this disturbance and converting this from the DQ frame to ABC frame, then this ITA, basically this ITA stands for the instantaneous current of phase A, that is what this ITA, small ITA. It looks like this, it has two parts. The first part is the fundamental component part, that is ID cos omega naught t, and the second part consists of two, that is cos omega 1 t and cos omega 2 t. Now, if you could see that what is this W1? The W1 is nothing, that is W naught plus WD. The WD is our fundamental disturbance signal frequency and W naught is the fundamental frequency. This WD is the disturbance signal frequency and this W naught is the fundamental frequency, the signal which is present, fundamental signal. If I know this W naught, let us say it is 50 hertz. If I will take F naught is equal to 50 hertz, then the corresponding this W1 I can always calculate, that is based on this F1 and this F2, how to calculate it, that is F naught plus this FD. If I will take FD is equal to 30 hertz, then it will be 50 plus 30 is equal to 80 hertz. that is my upper limit of this particular disturbed phase A signal, because I have already injected one disturbance signal to my controller for the as far as the d axis is concerned, right. And next this particular f2 is equal to omega naught, this is f naught I am taking, f naught minus f d, that is equal to 50 minus 30 is equal to 20 hertz. That means the range is basically within 80 hertz to 20 hertz. That particular signal phase A current, instantaneous phase A current lies, this frequency of the second component is between these two. So, lot many exercise can be done, and many parameters or quantities we can take, and we can analyze whether there is islanding or not. Now, after that we are going to measure the PCC voltage of phase A. So, this phase A voltage has two parts. The first part is V omega naught cos omega naught t plus V omega 1 cos omega 1 t plus alpha 1, and this omega naught 2 omega 2 t and alpha 2, where this alpha I is the basically the angle and this is expressed here r into this omega I c minus 1 upon omega I L, and this I is equal to basically 1 and 2. This is how this particular signal injection based technique provides the information about the current as well as the voltage of phase A. After this we will measure the voltage, that is VD, because as I said from the beginning, while we will inject this particular signal, that is ID, and again this ID is some percentage of the reference signal. Just if you see this figure, here we have taken first 0.5% or we can take 1%, 1.5% and 2%. We can vary the percentage of this ID with respect to our reference signal. After that we will see the impact at the PCC bus, that what is this value of this VD. This VD looks like this. After this islanding, you can see here up to islanding the signal is almost constant, it is steady, there is no variation, but after islanding the signal is going to oscillate with the frequency of at what rate we have injected, 30 hertz, 20 hertz, or we are just going beyond our fundamental frequency, it is basically 70 hertz or 80 hertz. So, this oscillation if we can trace, if we can track, then always we can say there is some islanding situation. Similarly, if you see by varying the frequency of the injected signal, if you see the second figure, that is we have taken 1 hertz, maybe we can take 10 hertz, 20 hertz, 30 hertz. Here we are just varying the frequency of the injected disturbance signal. If you vary that, again the pattern of this VD which is measured, basically estimated, that will also vary. So, based on this concept, we can always detect whether the system is islanded, this microgrid is islanded or not islanded. From there again this another parameter, or you can say indices, other indices are calculated. The first one is ADVV mean. This ADVV stands for mean of absolute d axis voltage variation, and this ADVV means absolute d axis voltage variation. This is, if you just keep it here mean, that is absolute d axis voltage variation mean, and here you could see that by taking within a single period 1 upon t, t minus t to t, we have calculated the mean of this particular voltage. What is that voltage? This is the difference of these two voltages, VD reference and the VD actual value. If you will take the difference between these two and then you will take the mean of this particular voltage, then you will get this ADVV mean. This is one index, that is one index which will be used to detect the islanding situation. And another index, another parameter you can say, we are just calculating directly from the VD voltage, the d axis voltage, that is AROCODV, that stands for this AROCODV stands for rate of change of absolute d axis voltage variation. We will take the dVt by dt. If you see this equation, what is that? D, a derivative of small v dt divided by dt. The rate of change of this particular voltage dx is voltage, instantaneous voltage. That is also another index to detect whether the microgrid is islanded or it is not islanded. After that, we will take mean of this particular voltage, the rate of change of Vd. If we take this mean, it will also another index. See why we are doing all this exercise, because sometimes what happens, if we take more number of features, I can say this, these are basically features. You can take voltage, you can take the mean of the voltage or rate of change of the voltage or energy present in rate of change of voltage, those are basically different features. Why we are taking many number of features? Because a single feature may not be sufficient to detect whether it is islanding or not, or it is non-islanding situation or not. It may happen sometimes that few non-islanding situations will behave like a basically an islanding situation. So, in that case, if you have more number of features, then it will be the final decision will be more reliable and more accurate. For that reason, basically we are just interested to have more number of features. Based on this, in this particular paper, they have formulated one logic diagram. The logic they have developed, these two features they have taken, and through this summer plus minus, this is threshold and actual value, the difference they have taken. If suppose the value of this particular feature exceeds the threshold value, then this timer will be on and this output will be given to this, the signal is going to given to this AND gate. And similarly, this feature, if the threshold value, the threshold the value of this particular feature is exceeding the threshold, then this particular signal will be given to this AND gate, right. So, this AND gate means if this particular status timer output is 1 and this timer output is 1, then only this two inputs, these two inputs are 1, then only this AND gate will operate and then the trip signal is going to be generated. That is what the meaning of this AND gate. If any one of this particular feature output is 0, that means even other one is 1, still there will be no trip signal, right. So, the output is going to be 0. That means together the two signals should be 1. This is how the they have just simulated the system and they have just kept few signals in front of us. So, we will just discuss it, and we have taken from this particular paper or article. You can say this, you can just download it and you can see and you can read more about it. In fact, to be honest, there are lot many papers are there, lot many research papers are there based on this active islandation technique. This is in this particular class we are just discussing one technique, you can follow many techniques. The idea may be different, but the concept everywhere same, like we are injecting some disturbance signal to the controller and then just we are measuring the parameters or quantities at the PCC bus. Now, if you see the first figure, that is Vd, that is in volt. You can see here this particular left side figure is for the islanding situation and the right side figure is for the non-islanding situation. This is the variation of this Vd, and you can see here it oscillates with certain frequency, and the corresponding first feature, that is AdVV mean, and this is the threshold, the dotted line is the threshold. And you can see here very clearly the computed value of this AdVV mean is crossing the threshold value. And similarly, here you can see for the second feature the value is crossing this threshold, and that is why this trip signal, the red dotted line is present here. This trip signal is now generated at this point. So, that is how, and you can see here this particular event is initiated here, but however, after 0.1 second this trip signal is generated. It takes some time to generate the trip signal. Now, coming to this non-islanding situation, see here the variation of this particular islanding situation and this corresponding here the non-islanding events. Everywhere you can see this particular variation of this AdVV almost below this threshold value, here also below threshold value. So, that is why the trip signal is almost 0 throughout. And you can see here, though this particular computed value of this RARCOD crossing this threshold, but however, at that time another feature is not crossing the threshold. That is why this trip signal is absent. As I said, the output of the two signals should be 1 1, then only this AND gate output will be 1 and the trip signal will be generated. So, though even one feature is okay and another feature is not satisfying, that is why this trip signal is silent at this point. And similarly, many authors, they have also injected current in the q axis, they have injected the d axis current through the q axis of the controller, and also they have seen this variation of the voltage and current. And if you see for this q axis variation, this is in the q axis current, they have just injected this ID, the ID current, and the corresponding phase A current just we have discussed in the previously for this ID injection current. Similarly, here the difference is that minus in place of plus, and you will get here sign component, and this comes due to the transformation matrix between this DQ frame to the ABC frame, that is all. So, you can always calculate using this transformation matrix. Now, we will have a good comparison, and here you can see that in case of this current injection based method, this DER operates in stable region and negligible NDZ. But in this case, as we are injecting some disturbance signal, this power quality of the system may be degraded, may be affected. Now, we will come this hybrid based detection technique, that is our passive island detection based technique. If you see, in case of passive island detection technique, basically the NDZ problem is there. Certain label is maintained, like for 15% power mismatch, above that this particular technique will work fine, otherwise this below 15% the technique is not going to respond. That is what the major drawback of this particular passive island detection technique. To overcome this NDZ problem, we have this active islanding detection technique. We have just discussed one, that is our basically the injecting the disturbance signal to the controller of this inverters of the solar or wind system. We can measure the parameters, or we can estimate the parameters, or we can measure the quantities at the PCC to decide whether the microgrid is islanded or not. And also we have positive feedback type active island detection technique. There actually we pass this voltage angle or frequency from the PCC to the controller to see the corresponding PCC voltage variation or frequency variation or power variation, whether there is islanding in the system or not. In case of positive feedback based active island detection technique, that is basically the NDZ problem is not there, but the DG, the DERs or the renewable sources are driven to a basically to an unstable mode of operation. That is a major drawback of positive feedback based active islanding detection technique. Now, similarly this for this hybrid system, what happens, we will just combine together, we will just have both passive and active techniques together, so that we can remove the NDZ problem, as well as also we can just try to minimize the power quality threat, or we will just minimize the percentage of this DG is going to be non-stable mode of operation. That is what the main aim of this hybrid islanding detection technique. Here I have taken one technique, that is basically voltage unbalance, that is V2 upon V1. This first feature, this one is basically the passive technique. This is passive islanding detection technique. This passive island detection technique, what we do, basically we took some parameters or we took some ratios of the voltage or current or frequency, maybe sometimes rate of change of frequency or some impedance measured at the terminal of this VCC. So, those parameters or quantities we can always take first initial indication whether there is islanding or not. If it is not islanding, so it is not necessary, it is not required to inject any disturbance signal to the controller of the inverter. That is what the main intention of this hybrid islanding detection technique. What we do basically, initially if you just see in case of active islanding detection technique, like first one, that is a signal disturbance injection method, there continuously we keep on injecting this disturbance signal to the controller, which is not desirable. So, every time our power quality has some problem, But in case of hybrid, what you do, initially first we will detect whether there is islanding situation or not, then only we can inject the disturbance signal to minimize the non detection zone problem. So that this particular NDZ problem which is not covered or tackled by the passive islanding detection technique, then we can always do by this active islanding detection technique. The passive basically fails for this NDZ. That is why the first step is to calculate here the ratio of this negative sequence voltage to positive sequence voltage, and if this particular ratio is exceeding particular percentage or threshold, then yes, there is some islanding present in the smart grid system or microgrid system. And this V2 is the negative sequence component of the voltage at the PCC, and this V1 is the positive sequence component of the voltage at the PCC. Now, after this, if you can see this flow chart, flow diagram, a logic diagram that we are monitoring this voltage unbalance, what percentage of voltage unbalance is there or present in the system. If it is within the acceptable limit, yes or no. If it is this VU, VU stands for voltage unbalance, VU over the acceptable limit, no. So, again you have to go back, yes, then change the frequency set point to DG from 60 to 59 hertz, this is important. If this is not this is this UV over the acceptable limit, yes, then we have to change 60 to 59 hertz continuously to monitor this frequency for 1.5 second. The duration of this frequency monitoring is 1.5 second. And after that is the DG, then we will just measure the frequency at the DG terminal. DG means the distributed generation, or we are calling it DER, distributed energy resource. Now, again another check we will do, that is this DG frequency is below 59.2 hertz, yes or no. If it is yes, then there is islanding. So, we have to generate the trip signal, and that trip signal will just open this circuit breaker at PCC, and again after that it will restore the frequency set point to 60 hertz. So, these are the steps. If it is no, then change the frequency set point to 60 hertz, okay, and after the UV spike. So, these are the steps basically maintained in this particular technique, that to just demonstrate in front of you that what is this hybrid technique. In case of hybrid technique, this is how this passive part, this is our passive islanding detection technique, and this part is basically we are just varying the frequency point of this particular DG system, where this is our active islanding detection technique. Together it forms basically the hybrid based IDT. Now, they have taken this particular system, and this is the result. You can see here that I just explain this part. See the frequency and frequency set point for DG1, they have taken 2 DGs, and these are the corresponding results. For DG1, you can see here at this point the voltage, the ratio, that is voltage unbalance, is crossing the threshold, and at this point here this UV is not crossing the threshold, very small values you can see here, and in this 2 cases basically you can see here it is crossing the threshold value. And due to this spike, they have also set the frequency point from 60 to 59 hertz. You can see here this is 59 hertz. And after this, when this islanding has occurred, now you can see, so very quickly this frequency is dropping to below 59.2. See here it is 59.4, 50, basically it is dropping quickly, this frequency is dropping, and immediately this 59 hertz is resumed to your 60 hertz. That is what this particular technique says. If any islanding is there, the frequency will drop very quickly below 59.2, then it is islanding situation. So, we have to reset this frequency to 59 to 60 hertz, and also we have to restore, and also we have to open this circuit breaker, and after that we have to restore. And similarly, this is for DG2 terminal. Here you can see here they have generated, they have just set the frequency value from this 60 to 59 for 1.5 second. Again here also same thing they have done. At this point you can see very quickly this frequency is dropping to below this 59.2 hertz, and at this point this value of this UV spike you can see here quite large, and that is why this it indicates there is some islanding situation. So, the summary of this particular hybrid based technique is, it is not necessary continuously we will just keep on changing or just giving some disturbance signal to the controller of the inverter. Rather, it is better if this islanding is detected once, let us start injecting this disturbance signal. That is what this hybrid islanding detection technique. Somehow we can reduce the power quality threat in this particular technique. Now, if we will come to this communication based techniques, there are many techniques are there, like first one is power line carrier communication, second one is signal produced by disconnect, and third one is SCADA, that is supervisory control and data acquisition based technique, and the fourth one is synchrophasor measurement unit based technique. Now, researchers are trying to have more access to this particular technique, because now we are moving towards smart grid, I mean the smart system, and there we need some smart technology, and where this time gap and the delay will be very less, and our decision will be very accurate and fast. And for that, this swarms based technology or synchrophasor based technology is basically one very good research field you can say, and there are many papers are also coming up for this communication based islanding detection technique based on this PMU measurements or micro PMU measurements. In many papers also you can see the grid eyes or FNet based techniques, and those are also communication based islanding detection techniques. From the phasors of the voltage and current, always we can measure whether we can decide whether there is islanding or not. That is what the main aim of this particular technique. Now, if we come to this power line carrier communication, that is PLCC, what happens here, the arrangement is shown in this particular figure. Here is our grid, and this T stands for transmitter, this R stands for receiver, right. So, this is our common coupling point, this point of common coupling, and this is our transformer, the PV inverter and the load. Now, the point is when let us say this grid is disconnected, this transmitter will send the message to the receiver that now this grid is disconnected, then this inverter technology, the controller will just shut down this particular PV system, so that no current is going to be driven from this, I mean no current is going to be supplied from this PV system to this particular load. That is what the meaning of this power line carrier communication based technique. And similarly, we have the signal produced by disconnect, it is almost similar to this. The only difference is the type of transmission used, like microwave link or telephone link or others, right. So, these are the few power line carrier or signal produced by disconnect based communication techniques. In case of SCADA, you just already we have discussed in the previous classes that SCADA supervises the status of circuit breakers which are present inside the microgrid or smart grid system. By knowing the status of the circuit breaker, we can always decide what to do and which component should be shut down and what is the status of the whole network, right. So, that is what this SCADA does. It monitors the auxiliary contacts, all utility circuit breakers, those are able to check the condition of the islanded operation, right. So, if it is islanded, if the main grid is islanded, so that particular breaker is open at the grid side, main grid side, that particular status will inform us that yes, now the microgrid is disconnected from the main grid. So, that is basically upon the islanding a series of alarm is activated and the corresponding circuit breaker is tripped, and then we can decide, we can take corresponding remedies. That is what the SCADA system. Now, the PMU based island detection technique, if you could see this particular figure here, we have considered this particular bus where one PMU is installed and here another PMU is installed, and these two PMU data are sent to this relay. Let us say this relay is our islanding relay or island detection relay, and this is our circuit breaker which is going to be basically triggered with help of this particular islanding relay, and this is our embedded generator or DG, or you can say it is basically the DER, and this is our major station, means our main grid system. And here is our basically the communication infrastructure. That communication infrastructure is very essential as far as the worms is concerned, where the 2 PMUs send their, I mean this 2 PMUs send the data to this relay through the communication platform, and then this relay will take the decision. Let us say for example, this particular major substation is disconnected and this breaker is open. Now, the voltage angle at this bus, positive sequence voltage and the corresponding angle information, this V1 magnitude and the corresponding angle, right. This V1 is the magnitude and this is the angle will reach to this relay. And similarly, this PMU also will measure this voltage at this bus, some phasor, that is some magnitude V2 with angle of phi 2. Now, when these two quantities like voltage of this particular digit terminal voltage and the voltage of this particular this grid main grid voltage will reach to this particular relay. So, what will happen? Then this relay will decide whether there is some islanding situation or not. You can see, you can simulate also this type of system, that when this is this embedded generator is disconnected from this major substation or grid, now very distinct angle difference will be there. The angle difference between this phi 1 minus phi 2 is very visible. it is kind of you can say del phi is very significant, right. And also we can also take the difference V 1 minus V 2. This voltage difference is also it is a kind this V 2 is not negative sequence, rather this voltage is the magnitude of this particular digit terminal bus voltage. Now, you can say either take the voltage difference or you can take the angle difference, and from there we can take many number of features. Now, why not only the voltage, we can also take the positive sequence current magnitude and phase angle, and from those features we can always take the final decision at this relay terminal, that whether we have this islanding is there or not. Now, let us have a general comparison of all the techniques. We have discussed active islanding detection based technique, and also we have discussed this hybrid based technique, and also we have little bit about this active in case of positive feedback based active IDT, and also this communication based IDT. Now, if you see, these are the passive islanding detection technique. In the previous class we have discussed the major the advantages like cost effective and no power quality issue. So, these two are the major advantages of this particular passive IDT. Now, if you see the disadvantages, the major disadvantage is the larger NDZ, this is important. So, we want to reduce this NDZ problem, and this particular NDZ problem can be reduced using this subsequent the active and hybrid or communication based techniques. Now, if we have also, you can see in the review literatures, that we have signal processing techniques like energy in signals, wavelet transform, S transform, and though this particular the lower NDZ compared to conventional passive techniques here and no power quality issues, but at the same time it requires higher processing of the signals, very robust and very compact, which will be physically it is implementable and we can implement in real field. That kind of signal processing techniques are desirable, right, and there we need higher processing of the signals, and for faster operation we need the processors should be quite compatible with the current trend. And coming to this artificial intelligence techniques like support vector machines, neural network, fuzzy systems, both neural network and fuzzy, there we need huge training data set. So, in that case also it is very difficult in practical implementation part, and those are some merits and demerits. And if you come to this, this is basically our active island detection technique. Here in case of active IDT, we have this negligible NDZ, right, and also this active IDT does not drive the system into unstable mode, this is important. But however, at the same time the power quality issues there, that is why we are worried, so that we are going to have some hybrid based technique, right. And here also we have some hybrid based techniques negligible NDZ, but at the same time what happens, the system is driven to unstable mode and the power quality issues to some extent present when the disturbance signal is injected, right. So, this is all about our the course. Today in this lecture we have discussed first the active islanding detection technique. As we know that in case of passive islanding detection technique, the major problem is the NDZ, the non detection zone problem, and that is why to overcome this we just went for active IDT. And in case of active IDT we have this power quality issues, though the system is not driven to unstable mode, but we have this power quality issues. And that is why again what we did, we just combined together this passive and active together to get this hybrid IDT. In case of hybrid IDT we have like what happens when this signal is injected, then the system may run in unstable mode. In case of communication based technique, we can overcome again this NDZ problem, but however in this case the communication infrastructure is very costly, and if some communication infrastructure failure is there, so we lose the data. So, today this much. Thank you so much.